All right, folks, let's go ahead and get started. I do want to welcome you back to this second installment of solutions. This is Unit 11. Last time we were talking about a couple of definitions involving solutions, including a solute and a solvent. We said the solute dissolved in the solvent, and that the solute generally was a solid and the solvent was a liquid, but it didn't have to be that way. For example, if you have Coca-Cola, carbon dioxide gas is dissolved in a liquid, right? So you can have a gas dissolved in a liquid. For a solid dissolved in a liquid, we saw that the trend was as we increase the temperature, generally speaking, the solubility was going to increase as well. There were a few exceptions to that rule, but for the most part, that was it. Increase the temperature, you increase the solubility. Now, again, it was just exactly the opposite for gases dissolved in liquid. Think of a Coca-Cola. But at any rate, the point is that if we take the more general case of solids dissolved in liquids, what we have is increase in temperature equals increase in solubility or rate of solubility. So we've already kind of discussed that first one, right? So let's now talk about crushing, okay? Folks, when I was a little boy, I didn't like to take tablets, medicines of any type, to be honest with you, but I didn't like tablets, right? Especially, they just didn't, and to be honest with you, to this day, I'm not crazy about taking vitamins and things like that, but I have to do it, so I do it. But the point is that when I was a little boy, my mother used to take a baby aspirin. Knowing that I was going to not want to take the baby aspirin, she would play a little trick. She would take the baby aspirin and put it on a spoon, and then she would take another spoon and she would crush that baby aspirin, and then she would take that baby aspirin powder and she would put it into some milk or some water or something like that, and I would drink that, and my fever would go away. But the point is that by crushing the baby aspirin, she was increasing the surface area of the solute, that was the baby aspirin, dissolved in the solvent, that was the water or the milk, right? And she was increasing the speed at which the solubility occurred, and therefore increasing the speed that I got better. That's the main thing, right? And so the point is that crushing is another way of increasing the rate of dissolving, all right? Of dissolving. All right. Let's talk a little bit about a concept called like dissolves like. What do we mean by like dissolves like? Well, essentially what it means is that polar solutes are easily dissolvable in polar solvents, and nonpolar solutes are dissolvable in nonpolar solvents, but they don't mix very well. In other words, polar does not dissolve nonpolar very well, and vice versa. Now let's go back and review what we mean by polar, right? What is a polar versus a nonpolar molecule? Well, a polar molecule would be something like water. So remember that water had two hydrogens, an oxygen, and then two lone pairs of electrons just like that. So there was a polarity to each of the bonds, but there was also a polarity to the molecule as a whole. The oxygen was more electronegative than the hydrogen, and so there was this overall polarity in the molecule. The molecule is polar. So water is going to tend to dissolve polar substances well, but not nonpolar substances. It's not going to dissolve nonpolar substances very well at all, right? So what would be an example of a nonpolar substance? Well, let's take something like hydrogen gas, right? Hydrogen gas is this. Hydrogen gas is just two hydrogen atoms with a shared pair of electrons between them. But the point is that they're identical on either side. That makes it nonpolar, right? So water is polar. Hydrogen gas is nonpolar. They're not going to mix very readily, right? Because of the fact that one's polar, one's not. And that's what we mean by like dissolves like. Okay, like dissolves like. So I hope that makes sense, all right? All right, substances which are readily mixed are called miscible. Okay, miscible and mixable are essentially the same, right? Oops, sorry about that. Okay, those which do not are called immiscible. So miscible is mixable, unmixable is immiscible. All right, that's how that goes. All right, so for example, water and carbon tetrachloride are immiscible. Water and carbon tetrachloride are immiscible. if I put water and tetrachloride together, you see how I have water on top and I have carbon tetrachloride on bottom because carbon tetrachloride is more dense than water. But if I put two nonpolar substances together, like iodine gas and carbon tetrachloride, they're going to mix very well because both of these are nonpolar, right? Both of those are nonpolar. All right, so note the first example is immiscible because water is polar and CCl4 is nonpolar. On the other hand, for the second example, both I2 and CCl4 are nonpolar. Now remember, like dissolves like. They are completely mixable or miscible. If you have two polar substances, they're both you have two polar substances, they're going to be mixable. Two nonpolar, they're going to be mixable, but you can't mix very readily polar with nonpolar. Now, we've talked about water already. Water is a polar molecule, therefore it's not mixable with CCl4, right? So this is the polar molecule for water. Remember, the electronegativity lies more towards the oxygen than the two hydrogens, so the overall polarity is going to be towards this oxygen, just like that, as opposed to the CCl4. Let me just draw a quick Lewis structure for that one right there. It's going to look like this. I won't bother with the lone pairs of electrons around the chlorine, but the point is it's the same in all directions, therefore it's nonpolar. Water and carbon tetrachloride, not going to mix. They're not going to mix readily, okay? So that's that. All right, I want to go back to solubility curves. We talked a little bit about these in the beginning, and what I want to do now is I want to look at how we interpret solubility curves and make sure we understand how to do this, okay? So let's look at a solubility curve and see what types of questions we can answer from a solubility curve. So here's one like this, okay? Remember, on the x-axis, we have temperature. On the y-axis, we have grams of the substance, whatever it is, like sodium nitrate, potassium nitrate, ammonia. Look, ammonia is an exception to that rule that as temperature increases, solubility increases, isn't it? See how it's going down like that? Here's another one that's going down right there. But they're few and far between. So let's see if we can answer some questions using this solubility curve. I'm going to try to increase the size of this just a little bit. Let's see. I can't do it too much though. All right, here we go. The first question is this. How many grams of potassium chloride can dissolve in 100 grams of water at 50 degrees Celsius? All right, so we're talking about potassium chloride. Let's go back up there, and we're at 50 degrees Celsius. So remember that number of 50 degrees Celsius. And remember potassium chloride as well. So here we go. So where is potassium chloride on this chart? You find it? There it is, way at the top, right? Way at the top. So if we go to, I'm sorry, it's not way at the top. It's right here, okay? So potassium chloride is right there. So if we go to potassium chloride, we look across, here's the potassium chloride line. That's where it hits the graph right there. I'm going to go right across, and what do we see there? About 40, right? So about 40, if I dissolve 20 grams of KCl in water, it's about 40 grams. If I dissolve 20 grams of potassium chloride in water, only 20, in 100 grams of water at 50 degrees Celsius, how much more can I dissolve? Well, the maximum you can dissolve is 40 degrees, right? That's a maximum you can dissolve. If you got 20 in there right now, you can do another 20 grams, and you're still just saturated, not supersaturated at that point. You're saturated at that point, okay? So you can put 20 more grams in there. All right, which of these substances is least affected by temperature? So let's take a look at the chart again and see which one is least affected by temperature. So if you look at sodium chloride, see how sodium chloride is almost flat, right? Almost flat. As you go from left to right, it's not increasing. It's increasing a little bit, but not very much. So in other words, it doesn't really matter for the most part what the temperature is, whether it's 10 degrees or 100 degrees. It doesn't really matter. You're going to be able to put about the same amount of sodium chloride to saturate, and so sodium chloride would be our answer, okay? Sodium chloride is the answer. All right, let's try another one. A solution contains 50 grams of potassium chloride in 100 milliliters of water at 10 degrees. So remember that 10 degrees. is this solution saturated, unsaturated, or supersaturated? So remember, 50 grams is what we've got. 50 grams is what's in there in 100 milliliters of water at 10 degrees. So what we're going to need to know is we're going to need to know the maximum level of saturation, right? Or the maximum amount of sodium, of potassium chloride in the water. So let's find the potassium chloride at 10 degrees and see what it is. So here's the potassium chloride right here. And we said 50 degrees. Sorry, we said 50 degrees. And so here it is right there. We go across, it's 40, right? 40 grams is the maximum amount. So, folks, you know what? I'm sorry, I was looking at the wrong temperature. We're supposed to be looking at 10 degrees. Let's do that again. So 10 degrees for potassium chloride. Now let's go down here. Sorry. So 10 right here, go across. That's about what? 32? Right? If this is 10, we go across. Here's the potassium chloride line right there. That's about, in fact, I would say that's right on the 30, just like that. Okay? That's right on the 30. So it says that I've got 50 grams. So at this temperature, the saturation limit is about 30 grams. So the solution is 50 grams. It's supersaturated, right? Because I've got 50 grams. Supersaturated because I've got 50 grams instead of 30. So something must have happened to allow me to have 50 grams instead of 30 grams. And we'll talk about that a little bit later, okay? All right, let's move on. Solubility of gases dissolved in liquids. So we've talked about the solubility of solids dissolved in liquids. Now what we're going to talk about is liquids or gases dissolved in liquids. The dotted lines on the diagram to the right are for gases dissolved in liquids. Do you see the difference? For gases dissolved in liquids, as the temperature increases, the solubility decreases. Just the opposite as for solids dissolved in liquids. So for most things, as you increase for most gases dissolved in liquids, as you increase the temperature, you're going to increase the solubility. If you increase the temperature, you're going to decrease the solubility. Again, for gases dissolved in liquids, okay? All right, so that's that. All right, folks, I want to talk a little bit about a very important formula, and that is the dilution formula. So we've all had experience with diluting materials. So for example, if I had Clorox, I wouldn't want to put straight Clorox out of the bottle onto the kitchen floor, right? I want to dilute it somewhat. So what we're going to do is we're going to look at a formula for dilution. And this is the formula. It's M1V1 is equal to M2V2. What does the M1 and the V1 and the M2 and the V2 stand for? Well, the M1 is the molarity of the more concentrated solution. The V1 is the volume of that solution, okay? The M2, of course, is the more dilute solution. The volume is the volume of the more dilute solution, okay? So essentially what we're saying is that the molarity of one solution, the more concentrated one is, multiplied by the molarity of one, multiplied by its volume is equal to the molarity of a second one, or a more dilute one times its volume. We're going to do some examples in just a moment. So you can make a more dilute solution by lowering the molarity from a more concentrated one, but you can't go the other way around. You can't take a dilute solution and make it into a more concentrated solution, okay? It doesn't work that way. All right, let's keep going. Tell you what, folks, let's go ahead and take care of this example on the next screencast. So I'll see you on that one. Thanks. Bye-bye.